All right. Again, this is Steve Marzoff, the Integrated Services Program Director here at VITA, and welcome again to our webinar Wednesday. We try and do these every couple of weeks to provide information out. Now, today we're going to do a introduction to LiDAR, and this is a presentation or a webinar that we've conducted before, and quite frankly, had hoped to record it then, but something got messed up with the recording, so we thought we'd offer it again because it was so popular. And this time, make sure we get the recording so people can actually watch the recording. But please, as an administrative reminder, please mute your phone. We can mute everyone, but we'd really rather not do that so that you can ask questions. We need you to mute your phone. You hit *6 if you want to mute through the conference bridge, or just mute your phone with the mute capability on the phone itself. Please feel free to ask any questions that you may have as you go through, or it will save time at the end to be able to ask them as well. So today we got John Scrivani. John has 30 years with the state, working in various GIS jobs, but currently is our geospatial program manager, and has been lead with our elevation project, which is in large part LiDAR acquisition and coordinating with federal partners as well as local partners in the acquisition of data. So again, please mute your phones so that we don't get the background noise, especially in our recordings. And with that, I'll go ahead and turn it over to John.
Okay, thank you, Steve. I hoping everybody's seeing the title slide, Introduction to LiDAR in Virginia.
We are.
Okay, I'll proceed. So what we wanted to do today, let's see, is to give you a brief introduction to LiDAR and some of its applications in GIS and various applications in public safety and urban planning and lots of fields, actually, forestry, resource management. But what is LiDAR? So LiDAR is an acronym for light detection and ranging. So it's designed a little bit to be similar to radar acronym, but LiDAR uses laser pulses instead of radio waves to determine distance to an object or surface. In the type of LiDAR that we use for elevation services and features on top of the surface of the Earth, it's typically collected using a system that consists of a aircraft-mounted laser pulse scanner to send and receive the data, aerial GPS systems to determine the precise aircraft position, and then an inertial measurement unit to measure aircraft attitude, pitch, yaw, and roll. And that enables the system to exactly locate in XYZ locations wherever the laser pulse hits the ground or feature above the ground. It's a scanning system, so as the plane flies along its flight line, it scans back and forth across from an angle, left and right, and the light laser pulses are reflected and go back to the unit in the plane and are recorded. The advantages of LiDAR are very high resolution elevation data. So 1 meter or less data spacing. We typically have several points per square meter. This is in good contrast to what has traditionally been done with photogrammetric methods, where you may only have mass points several meters, if not tens of meters apart. So you have a lot more detail. You also have very high vertical accuracy. The data we collect typically we have collected in Virginia, are typically 10 centimeter root mean square error in the vertical dimension. And this is much higher than what was done on the old topo maps, which were, rather than 10 centimeters, were more like 5 to 10 meters in vertical accuracy. So the other advantage of LiDAR, it's able to penetrate vegetation and detect ground surfaces. So even with photogrammetric methods, if you had very dense vegetation, you were pretty much just guessing at what the elevation might be underneath dense vegetation. But the laser pulses, as we'll see in the next graphic, I believe, you can get through even fairly dense vegetation and detect the ground. You also get returns about and information about above ground objects, whether they're buildings or trees or forest canopy. So one of the reasons it's able to do this, penetrate vegetation and get more detail about above ground features, is that you can get multiple returns for each laser pulse. So the first return is whatever it first hits, but if a little bit of that laser footprint can get through the vegetation, it can go on down and hit another branch, say in that tree, or a third branch in that tree, and so on. And eventually, hopefully, some portion of that gets down to the ground, and you get a ground returned as well. So most of the data we have has multiple returns of 1 to 5 returns per pulse. So what are the benefits of LiDAR? Well, USGS had commissioned Dewberry a few years ago to come up with a nationwide cost-benefit analysis for LiDAR. And Virginia participated in that. I got together a group of folks from various state agencies and local governments to query them on what they saw as the economic benefit of higher accuracy elevation data. And the nationwide, and all the other 50 states did that as well. And what they came up with was an estimate of annual benefits between 1.2 and nearly $13 billion, and a cost-benefit ratio of 4.7. And they looked at various quality levels and various schedules of collecting the data, and they found it's kind of the sweet spot with the best cost-benefit ratio was quality level 2 data, which is that 10-centimeter accuracy, in about 0.7 meter spacing between laser pulses. And they recommended that be recollected on a 8-year refresh cycle. So my personal feeling, since that study was done about 4 years ago, that our group anyway was not as familiar with LiDAR benefits, and that a lot more things have come up that would probably increase the cost-benefit ratio. But what we did come up with was a expected annual benefits in Virginia of $10.3 million a year. An estimated total cost to collect the whole state at one time was at $13.5 million. So the payback period was only at 1.3 years. And then if we did also get a pricing for a quality level 1 biop if you wanted even denser data, which we did not really find to be as good a cost-benefit ratio. But our estimates in Virginia ranked urban and regional planning, natural resource conservation, and flood risk management. And I'd still say those are probably the biggest three. But we also have mining, agriculture and precision farming, infrastructure and construction management, geology, water supply, forest resource management, and coastal zone management as listed as benefits to Virginia. So it'd be ideal if we could get this data all collected in 1 year and get it refreshed every 8 years, but we haven't been quite able to do that. So since 2010, there's been a number of projects that have been funded primarily through the USGS 3DEP program, which has been a partnership with federal agencies, various federal agencies, some state agencies, some local governments, and we've been able to acquire nearly 3/4 of the state, or in process of acquiring nearly 3/4 of the state. This map here shows the area in gray as existing LiDAR that was collected between 2010 in 2016, according to the USGS specifications of quality level 2 for the most part. We do have a little bit of area in the east that was collected in 2010 that is quality level 3, but it's actually fairly close to quality level 2. We also have 2 projects. One is actually in progress right now, which is the listed here on this map as a FEMA proposal, but it was actually since then it's been approved and started, which collects a good bit of that southwest area in green in the southwest of Virginia. We have also VITA has put in a proposal under the 3-DEP program for funding for next year for the area that's showing up in that light orange color. And we have not received approval on that yet, so that is still tentative. But that we had good participation of partners with NRCS and the Virginia Department of Transportation on that, U.S. Forest Service, and a few others. So we've completed, actually I can update this a little bit with the latest data that's been delivered, but we had about 72% of the Commonwealth, and it's up closer to 76% now, and we've spent about $8.5 million, or USGS and others have spent about $8.5 million to collect the data, which has fallen in pretty closely, in fact a little bit under the original estimate. We've had funding partners participating. USGS, FEMA, and NRCS have contributed a large portion to a number of projects. The National Geospatial Intelligence Agency as well, to the Norfolk area project. DEQ, Division of Mines, Mineral and Energy, Nature Conservancy, University of Virginia, ODE, and ODU, and then some counties, Page County, Fairfax County, and then the Hampton Roads Planning District Commission and Hampton Roads Sanitation District contributed to that particular project. So if you want to see where we have projects, get a little bit more detail, you can, well actually, I guess that's the next slide, excuse me. So this is actually, let me go back. Here's the web status map, I'm sorry. This map, is hosted on our ArcGIS Online Virginia GIS Data Clearinghouse. I don't know if anybody can confirm that you're seeing the map. I think that should be what's being shown.
Yes, we can see it.
Okay, thank you. So this map, you can, I need to update it with the FEMA project, which is being collected. So once it's collected, I'll update it. But you can zoom around, you can search to find a place, but you can click to find what the particular project is. So if you were interested, for instance, in the Eastern Shore of Virginia, you could click on this, and you find that there's actually 2 projects for the Eastern Shore. One was collected in 2010. And then there was a second one. Oops. I'm not sure what happened there. Hide that. And there should be screen. I think there's a little bug in this program. I'm not showing the second project. So let me click over here and show the Hampton Roads project. And so that was collected. Yes.
Your screen's not being shared right now.
Okay. I don't know what I accidentally clicked on.
There you go. You're back. Thank you.
Okay.
Yes, it is.
Sorry about that. Thank you. Okay, so this map, you can keep track of what projects are have been already collected and delivered, and you can get more information about them by clicking on them. So like this one here, this actually I do need to update. It was collected actually in 2016, finished collected in 2016, and it's been delivered actually as of yesterday, and I'm getting that up on our download site. So let me switch back to the presentation. So if you want to get a hold of data, there's two locations to get it. One is the USGS 3-depth viewer. Let's see if I can get that loaded in. So this is part of the National Map Program, and you can, for instance, search for a location here. Oops, not Richmond, California, Richmond, Virginia. And then you could click on Find Products, and it would show you that you have the LiDAR point cloud that was collected in the 2014 Virginia post-Sandy project. And then you also have associated products from that, which is the National Elevation Data Set digital elevation models. So you can click and get the footprints of the different tiles and the metadata, and actually download the data as well. From the USGS site, everything is delivered in UTM coordinates, and elevation units are meters. If you prefer or want to get the data a little bit sooner for some of these projects, there is also a option to use our FTP site. So, for each project we're under development, we're actually putting a map interface to the FTP site. So here's an example that's what's working right now, which is the Eastern Shore, Virginia 2015 project. And that's a web mapping application, which I'll open here. And there's a little splash screen that tells you what the project is about. So it was a LiDAR project to produce high-accuracy elevation products. Everything was tiled in the standard LAS data format. It has 3D break lines and 2.5-foot cell size. So I'm going to close this splash screen. You can do an interactive download, zoom into an area, or search for an area of interest, like say you were interested in the Accomack County Airport. You could click on that tile, and you could click on download for the DEM or download for the ZLAS, which is a compressed version of the point cloud format. You could also get a zip file of the metadata, or you could click on a zip file of the break lines, which are 3D vector features that are used in hydro flattening, creating a good, a nice looking and hydro flattened digital elevation model. You could also click on this link to get the project report in PDF format. But some of the key metadata is right here, like when it was collected, what the quality level is, and what the nominal point spacing was, 0.66 meters. This project was actually tidally coordinated, meaning it was required that the data was collected within 2 hours, plus or minus, of low tide, and it was collected in the Virginia State Plain South Zone with survey feet. The other thing, and this is available actually for every project that we have data delivered, is a FTP browsable folders. So if you click on that, it takes you to the folder, which has all the data that you can get off the interactive map in just folder form. So the break lines, the metadata zip file, the digital elevation models are in here. and you can either download these individually or use some browser extensions which allow you to download all the files if you so desire. And the ZLAS files are in this folder. And you might notice if you're used to using the BBNP imagery, we get the data delivered when we can, at least, in the same tiling scheme. So if you know what ortho photography tiles you need, you can also just get the LAS files that correspond, or the DEM files that correspond to those same ones. So let me go back to the slideshow. So that was a data download demonstration. Using LiDAR is definitely a new thing. It's not. It's very different than typical raster or typical vector data. I guess technically it is vector data because it is points, but there are many points. So it's called a point cloud. And they can be used directly in some ArcGIS applications, or they can be processed into surfaces, either digital elevation models or TIN-type surfaces. The surfaces, when the data is delivered, it's usually, or it's always classified to ground and non-ground. Sometimes it may be further classified, but the points that are representing the ground are identified, and you can use those points to create a bare earth surface. But you might also be interested in creating a first reflective surface, what it first hits, whether it's the top of a tree or the top of a building. Bare earth surfaces can then also be used to produce contours. So the bare earth DEMs that are produced are raster digital elevation models. They use the LiDAR points classified as ground, and then the 3D break lines that are also delivered from the LiDAR project. And it produces a hydro-flattened representation of the ground surface. It's not hydro in force, so it doesn't necessarily show you exactly how water will flow over the surface, but it takes larger water bodies and rivers and makes them flat, so they're more pleasing, because the LiDAR points, LiDAR is actually usually absorbed by water, or it's kind of scattered by water, so you get a very rough-looking, or even a void where water is, or a rough-looking surface. So this is the reason why they like to have 3D break lines to flatten the surface. But the bare DEM produces a very dense and highly accurate topography, and it can be used to produce contours. So try and demonstrate the of course, I waited too long. Okay, let me confirm. Can somebody confirm that you're seeing a map?
I can confirm we're seeing a map.
Okay, thanks. All right, so this is actually the Eastern Shore project, and this is a mosaic data set built of all the digital elevation model tiles. This is a quick way to see an entire project, and actually a way to do a lot of elevation analysis can be done on the DEMs, particularly when they're put into a mosaic data set. I'm going to zoom into a bookmark area to show you the amount of detail you get in a digital LiDAR produced digital elevation model. And I don't know if folks know about precosins, which are very shallow depressions in a lot of the coastal plain of the southeast, but you can actually pick these precosins out on this imagery, these kind of oval areas, very easily, which is they're actually very hard to even see when you're on the ground. So you have a very detailed elevation service here from the digital elevation model. Actually, as it's redrawing, it's first drawing the point cloud, and then it's going to draw the digital elevation model on top of it. And so you get very detailed. You get all the roads and even the kind of the furrows in the fields. The other thing you can look at is the point cloud, as I mentioned. this is viewed in what's called in ArcGIS a last data set, which is a collection of the last tiles. But only 4.5% of the points are being shown at this scale. You have to zoom in really close to get 100% of the points, because you're talking about several points per square meters. In this scene, there would be many thousands, if not hundreds of thousands of points being shown. Let me zoom to another area. So this is town of Chincoteague, and I'm seeing right now I'm seeing all the points, and I can do a couple things with it. I could first go ahead and just look at the ground if I wanted to, and you see not much, but you're actually where the point where the laser points hit buildings. You see voids because they're not classified as ground. I'll switch that back to all. And I'm viewing this as a point cloud right now. I can also view this as a tin model. Which may take a second or two to draw. So here's more of a shaded tin model. I think I'll zoom in a little bit before so you can start to see and I'm still actually only seeing 16% of the image. It's going to get a little bit more detailed. I just jumped up to 44%, but there's actually more detail than you're seeing. It's just difficult for ArcGIS to draw that. I can also do a 3D view of this. Pick an area that has a few bird strikes. I needed to filter. Let's see. Let me maybe choose another area that works a little better. So I'm actually viewing all points. This probably could stand a little more filtering to get points that are very high, which are usually at least referred to as bird strikes. Well, let me just zoom in. Oops. Darn, picked that spot. Let me first do the profile. So I'm going to pick an area, say here, and I'm drawing a line, and I'm drawing a little bit of a rectangle around the line. But I'm seeing the building and vegetation that I've seen the ground points down here and the buildings and vegetation around it. Let me zoom back to a little different area. Let's see if this works a little better on the 3D viewer. A little bigger area, taking a little more time to draw, but so I have a 3D viewer that I can look at it at more detail. Actually seeing a power line coming across there, and so let me draw another 3D profile across. I think these are some buildings and some trees. Yeah, so that's a little better choice. You see the actual roof outlines, and then the trees, and then the ground points down here. A lot of things you can do with the LiDAR data, a lot of analysis that can be done, but certainly gives you high accuracy elevation data and then information about above ground features. The points can also be further classified. The USGS does typically not do any additional further classification, but you can classify them to buildings and vegetation points. And let's switch back now. to, let's see. That's what I wanted to switch to. So as we kind of saw on the map, that there are large collections of 3D elevation points with X, Y, and Z, along with additional attributes, things like the intensity of the laser return, which can be used. The other point cloud, actually each point has its X, Y, Z coordinates, the intensity of the return number, the number of returns, and then if there's a classification to ground or water or noise or buildings or vegetation, and then the GPS time, scan angle, and scan direction, a few other things. You can, if you have imagery that was collected at about the same time, you can further process the data and actually add the color from the ortho imagery to the point. And so you can actually look at these points in the natural color of the surface it hit, which is a pretty nice way of looking at it. It looks like an actual 3D model. So there's various options for using and viewing LiDAR data. I went through some in Esri, which is the DEM rasters. The way to handle the last tiles, you can look at those individually, but it's if you have a large project area, we typically get those delivered in 5,000 by 5,000 foot tiles. So if you want to look at a larger area, you want to put them into a last data set. You can also process the points and put them into a terrain data set, which may have some advantages for 3D analysis. You can also bring either the DEM rasters or the last data sets into mosaic data sets, which results in, when you use the last data sets, it results in an on-the-fly rasterization of the point clouds. It's a very efficient way to quickly look at a lot of LiDAR data. But if you really want to do a lot more with your LiDAR data, it might be worth looking into some LiDAR-specific software. LP360 is a commercial product that a lot of people use. Mars is another one. TerraSolid is actually one that's used by the LiDAR processors a lot for a lot of more detailed work. There's a public domain product called Fusion and another partly public domain product called Last Tools that allow you to do more with your LiDAR data. So went through the point cloud and talked about last data sets already. Just a little bit more on the USGS 3DEP program. This is an opportunity to partner with the USGS to acquire higher quality 3D elevation data. Most of the projects we've had in Virginia have gone through this program and have been not only gone through this program for funding, but also for the actual project management when we have USGS use the USGS Geospatial Services contract. And then we have worked with various partners in the state to come up with matching fund. This is actually a little dated slide. The next opportunity actually has already passed, and we submitted a proposal in October. The data that's collected under the 3DEP program all meets this data standard. This is the latest version, 2014. And it talks about the quality levels and how the data is processed and how the data is classified. We added a few kind of extensions to that standard. We came up with a LiDAR acquisition plan, which was adopted by VITA and VGen in 2014 to kind of guide our efforts in getting statewide coverage of LiDAR. It provides a role for VGen in just project coordination and data management. And it also added some specific data requirements that we like to have met for Virginia projects. And then we set out as at least our goal is to have an 8-year refresh plan. I guess we're in the first acquisition, 2010 to 2016, we have about 3/4 of the state done. So our additional specifications is that we like to have whole counties collected when possible. We like the data delivered in the EBMP tiling scheme. The DEM we like to have in a 2.5-foot cell size. If there's tidal areas in the project, we want it coordinated with the tides to be within 2 hours of low tide. We want the most current datum of North American datum 83 and the North American vertical datum of 88 with the most current geoid. And then the coordinate system we like delivered in Virginia State Plains, whichever zone, north or south, is appropriate for the project. That's the quick overview of LiDAR in Virginia, and certainly, I guess, Melissa, can we open it up for questions? Is that?
Absolutely. Anybody have any questions for John? You're making it easy on John. Come on, you got to make it a little more difficult. You got any technical questions or about either the data or LiDAR itself?
I got a question.
Go ahead.
Can you hear me?
Yeah.
For Q2 LiDAR, what's the most appropriate contour interval with the data?
Yeah. Good question. At 10 centimeters, that vertical root mean square error, that will support 1-foot contours.
Okay. Great.
Yeah.
I'll just go ahead and mention, too, that one thing about the contours, because of the density of the data, they appear much more ragged than photogrammetric contours. They're actually, in some ways, more accurate, but they're not necessarily cartographically pleasing. So a lot of times folks get contours made and then smooth them. The digital elevation models are often the better thing to do analysis with rather than contours, but people definitely want contours for cartographic purposes. So if you're getting contours which you can generate on your own from the LiDAR data, or you're having somebody produce the contours from it, you want to think about how much you want them smoothed, which generally loses a little bit of information but produces a more pleasing product.
Do you all have any suggestions on smoothing the contours? Should you smooth the surface or create the contours and smooth the contours?
There's different schools of thought on that. I find that if you probably want to start with the digital elevation model, which has already smoothed the data to 2.5-foot cells. And if you then need to, if you feel you need additional smoothing from that, you can use some smoothing algorithms. But yeah, I would at least do that rather than directly from the point clouds. But there's other folks who disagree on that. So
yeah.
Yeah.
Thanks.
Sure. Any other questions?
I have a question about bathymetric data. Does this LiDAR data set support any kind of underwater contours?
No.
Or the water surfaces?
Not the standard product that we get for elevation services, which is using the laser pulse is actually in the near infrared wavelength, and so it's pretty much absorbed by water. So you get voids in water unless there's something on the water, or you get specular reflection off of wave tops or something. You don't get really any penetration. There is a green light LiDAR that is used to try to penetrate water, but there has been data that's been collected by NOAA along the Atlantic coast, and that data is available. I didn't go over it here, but you can get that data from NOAA. But unfortunately, in the waters that we have in Virginia, for the most part, you don't get very deep penetration because of turbidity or wave action. but there is that's a separate kind of project that has to be done, and there is some for the Atlantic coast, but not for the Chesapeake Bay shoreline, unfortunately.
Thank you.
Sure.
Other questions for John? Speak now or forever hold your peace. Well, first, thank you, John, for doing the presentation again for us, and also to everyone who's participating. If you do have any questions that come up, John showed you where to get to the data, and if you haven't looked at your data and you have data, realizing we don't have it statewide, go ahead and there are a lot of things that you can do with it. It is highly accurate elevation data. If you do have any questions about it, you can reach out to your regional coordinator or to any of the VITA ISP staff. And if I'll give one last chance for questions, if not, thank you all for participating and have a wonderful rest of the day. Bye-bye, everyone.